Purpose of this lab was to use conservation of energy to predict the behavior of circuits which contain different combinations of resistors, ammeters, and voltmeters, using multimeters to measure the values of current and potential difference in a real-life circuit. The fundamental principles and models were used were Kirchhoff's law of node rule, and loop rule, which you can see are displayed on the left. Ohm's law, which says V equals IR, and resistors and capacitors in a series and parallels, and conservation of energy and charge. Preview of the results. The values found out of current and voltage differ slightly from the values we predicted using the formulas. This is likely due to some resistance present in the wire and not the exact EMF and battery. Based on calculations we used in an RC circuit, the magnitude of current is dependent on the time as predicted by the exponential equations of the RC circuits, which are displayed on the right. And models, we use components in real life to create the model of a circuit in order to observe current, voltages, resistance, and capacitance of a circuit in different combinations. The assumptions we used were when we calculate using formulas, we assume that the resistance of the wire and an ammeter is negligible and the resistance of a voltmeter tends to infinity. For our experiment, the system was the circuit, the surroundings were everything else in the room. For part 1, we used a circuit with two 1.5 volt batteries, two resistors, 47 and 100 ohms respectively, and two ammeters. The predictions we made were that I1 would equal I2 as per Kirchhoff's node rule, and I equals V over R, Ohm's law. R would be 47 plus 100. I equals 3 over 146, 3 being V and 146 being R, which came out to 0.02 amps. What we actually ended up getting was 0.0172 amps on I1 and 0.0171 amps on I2. That's correct. The actual currents were very close to the predicted values. The difference was so small that it was pretty much negligible. If we reversed it, the readings would be the same magnitude, just negative because of the opposite direction. If we replace the ammeter with the voltmeter, we'd get 3.07 volts and no amps. This is because the voltmeter has an extremely high resistance near infinity, making the circuit such that the current in the circuit is negligible. So the ammeter reads A, and as stated in the loop rule, where V equals V1 plus V2, the voltmeter will show 3.07 volts. All right, so for the experiment continued, this graph represents the different measurements of voltage for different components in the system, like the battery. And so you can see for BA we have 2.66 volts. DC we have negative, we go down by 0.85 volts, and then FE we go down by 1.79 volts. And you can see that's represented in the graph on the right. And FE and DC are going to add together to equal BA. Experiments and the calculations, we connected an ammeter in parallel with a 100 ohms resistor. Since I equals V over R, R being 47 ohms equals 0.85 volts over 0.0179, which equals 47.48 ohms. And R for the R for 100 ohms ended up being 100 ohms, and this is because the ammeter was in parallel with the 100 ohms resistor. Observations: we have a 10 ohms bulb, 20 ohms bulb, 9 volt battery, and a 200 mF capacitor. Battery was connected to the 10 ohms bulb and the capacitor in series. The bulb started at max brightness before gradually decreasing. That was the capacitor charging until 0 when the capacitor was fully charged. When the battery is disconnected, the bulb once again lights up and decreases until going out because it's discharging. I decreases from max to 0. For the 10 ohms bulb, it took 10.8 seconds to charge, 12.7 to discharge. And for the 20 ohms bulb, 17.6 to charging, 22.6 discharging. Y equals negative 0.18x plus 0.163, and we converted the exponential equation into a log, so we can get it in a straight line to compare on the graph. Equation negative 1 over RC equals negative 0.18 meters. We found that RC equals approximately 5.55 seconds, but while the expected value was 6 seconds. Discrepancies and errors in the model and the possible sources of errors, we have there's always a difference between the values predicted with formulas and values found using circuits. This is because in real life some resistance between the wires and ammeters will always exist. The battery also does not have exact EMF, and the voltmeter doesn't have infinite resistance either. Some current does get through. If you do in the lab in real life and you use an actual ammeter instead of an ideal simulated ammeter, the ammeter would have zero resistance, so the values we will get would still be very close to the values predicted by the formulas, as the ammeter takes up almost zero voltage. What if you were doing this lab in real life and you use a real battery to charge a real capacitor with no real resistor in the circuit? It would take more time than predicted, as represented by RC, because even the wires will have resistance. Thank you.